Okay, good afternoon, everyone. We're very happy today to have Owen Gwilliam from University of Massachusetts at Amherst, who's going to tell us about a bulk boundary correspondence for factorization algebras. Owen, please.
Yeah, so thank you for the chance to speak. I want to preface this by saying should be a very open-ended talk. Please redirect with questions. There's a lot of different ideas that intersect in what I'm going to discuss, so I'm happy to kind of pivot on direction. So I want to start by, some people may have heard me or others talk about factorization algebras before, but I want to foreground sort of a takeaway message, which is at best a 0th order kind of approximation to the ideas I want to discuss, but I think it's very helpful to have in mind. And then I'll give the plan of the talk. Okay, so the takeaway message is that the observables of a quantum field theory are encoded by a factorization algebra. Okay, so let me make a few comments. So first off, this is not a statement, certainly in mathematics. There's a sort of silly reason, which is that I haven't told you yet what a factorization algebra is. The less silly reason is that quantum field theory is a topic, as many of you know, that has not yet obtained, I think, its mathematical, correct, complete mathematical treatment. There's lots of wonderful stuff, but it's all very partial. So we're trying to compare something that's an idea from physics, which is still amorphous and shaping into mathematics, with an idea that you don't know yet. Words like encoded by are not really a part of a mathematical statement. But the philosophy, if you want, is that I'll tell you what a factorization algebra is. That's a very precise notion in mathematics. And for a certain type of mathematician, that is a good surrogate for thinking about the observables of a QFT. And so part of the goal is to see how much of the folklore around QFT is captured by things related to factorization algebras. So, like I said, this is not precise yet. There's sort of maybe two steps to this talk. So to this introduction. So one is to introduce these. So define and motivate. The second thing is you need to understand this, or sort of describe this, even if it doesn't admit a complete mathematical axiomatization yet. And we'll give a much more precise version of this takeaway in a few minutes, once we pin down what we mean by this side, and once you've learned what this side is. Okay, so you need to unpack those two pieces. So part one of the talk will be to introduce factorization algebras and their simpler cousin, which are pre-factorization algebras. If you've seen sheaves and pre-sheaves, this should be kind of reminiscent of that setup. After we do that, we can describe a sharp version of the takeaway. But in a special class for manifolds without boundary. Okay. And then I want to describe, now that I've pointed out that we talked about without boundary, describe a version for manifold with boundary. Due to Eugene Rabinovich, doesn't encompass every example of QFT for manifolds with boundary, but a fairly large, useful class of them. And there's some nice sort of applications and examples. So key example, a version of the Chern-Simons WCW correspondence, which is formulated in terms of factorization algebras. There are some, including higher dimensional examples for abelian case, for abelian theories. Another key application is, this is work in progress. So maybe I should just sort of say, this is a version of this for abelian Chern-Simons and U1 currents, or abelian chiral currents, is work done with Brian Williams and Eugene Rabinovich. Doing the non-abelian version carefully is sort of work in progress at the moment. Another bit of work in progress is showing that, sorry, let me erase that. A universal property of BF theories. So when you use these techniques and you study theories of the flavor of a BF theory, they actually have a universal property with respect to factorization algebras. And that's work in progress with Brian Williams and Greg Jeannot. And another application, which might be my preference for how to continue the talk since it's the most recently on my mind, is encoding defects. Things like Tufts lines or Wilson lines in gauge theories, or surface defects or things like that, using factorization algebras. So this is sort of an enhancement of the way we usually historically have talked about this takeaway message, that you can use factorization algebras to talk about not just sort of the simplest class of observables, but also things like disorder operators and defects, at least in special cases. Okay, so yeah, so that's the outline. We're gonna sort of set the stage, give some background for what this dictionary between QFT and factorization algebras is, and then we'll move on to manifolds with boundary, and we can pick some direction to go in. Okay, any questions so far? Awesome. So let me start by talking about pre-factorization algebras. Great. So I'm going to do that by, I'm going to give a definition, but I'm going to interpret it on the side in terms of sort of the language of QFT if you want. So please interrupt, because this I may be trying to do too much at once. So let M, I'm just going to work with manifolds. You can work with other kinds of sites if you want. Be a manifold. A pre-factorization algebra on M. So it lives on M. It's like a sheaf or something. It lives on a certain space with values in, well, you could take any symmetric monoidal category, but let's say in vect, or I often like to do DG vector spaces, like chain complexes. Consists of the following set of data. So first off, to each open set, U and M, there's some vector space or chain complex. So you should view these. So let's picture this. I'm going to draw the picture where M is maybe R2. I'm going to draw a little ball in R2. And what we have here is the observables or the measurements. So f of u, you should think about as we're kind of thinking in a quantum context. So there's this is the vector space of measurements you can make in U. So I don't know, operationally, you can imagine there's, some machines that happen in some region of space-time, and you kind of put them together to form a vector space. Okay. To each, let's do the easiest case first. So to each inclusion, one open set into a bigger open set, a linear map of V. So, if we have a bigger region V, then a measurement inside of U is also a measurement inside of V. So we could view a measurement in U as a measurement in V. No big deal. The more interesting thing is to any finite collection of pairwise disjoint opens, let's call them U1 up to U1 inside some V. So I'm going to draw a picture for you here. Got some big open set V, and then maybe I have U1 here, U2 here, and U3. A linear map so this is why we call it a kind of algebra. I can take a measurement I do here, a measurement I do here, and a measurement I do here, and they give me a measurement on the big open set. So I'm kind of multiplying the operators from different open sets together to get something on the big open set. Okay. So this is why it's called an algebra. And if you're inclined this way, there's a very efficient way to organize some of this in terms of instead of doing all this stuff I'm writing down, you write down a colored operad, and you're looking for a prefactorization algebra as an algebra over this colored operad. Okay. Such that, so I give you some data, and then I'm going to outline the sort of conditions it needs to satisfy. So I'll call these structure maps. So there's an associativity constraint, and here the idea is very, I think, relatively clear. We want composition of these maps to play nicely. So if I take the tensor product over I equals 1 to n of the UIs, then it could map to some, say, intermediary thing, j equals 1 to k. So I could have like a V1 here, maybe a V2 with some, 4, V5. But I can also think about the f of u's as going into some really big open W. And I want this to commute. So composition is well behaved. Again, if you're a fancy person, you can ask for this to be associative up to some sort of filler. So homotopical version of this idea. That's one condition. Let's say equivariant under relabeling. What I mean by this is, I have these actual open sets, and I gave them indices just to organize them. I called this the one, the first one, the second one, the third one. I could, of course, without changing what the open sets are, change the labelings on them. And so what I mean by that is if you chose to re-index them, that changes the order in which you write this tensor product. So that amounts to sort of applying a kind of swap map to these tensor products. And I want the map from when you relabel to sort of be the same up to that, applying that swap map. So if I just permute the labels, the map gets swapped. Okay, great. I think that's everything I had in mind. And I hope it's clear that, I hope you can see why you would expect that for the observables. Sort of, there's some way of combining observables in different open regions into bigger regions, some measurements you can make into big regions. And it's sort of just bookkeeping to sort of label the regions in some order so you can write them down explicitly left to right on a piece of paper. Okay, questions so far about motivation or about this definition? So,
sorry,
a great,
Owen, just
yeah, please.
a very simple question. So you want observables, and that's why you get vector space. If we're talking about states, of course, it would be something more elaborate like Hilbert spaces and so on. But you do want vector spaces for your definition, right? That's the idea.
So I think the target category, yeah, has to do with the class of examples you're interested in. So I guess as a remark, I should say, there are examples just purely from topology. Here's an example purely from topology. Okay, so let X be a pointed or based topological space. Okay, M is, say, a manifold of dimension n. So let me give you a factorization algebra. So here's a factorization algebra. Then the functor, I'm going to call it map sub C into X. I'll just describe what it does on opens in M. Goes to topological spaces. It sends U, goes to compactly supported maps from U into X. What do I mean by this? I mean that F is a map into X, and the pre-image of X minus the base point, the closure is compact. So it's, you know, if X were a vector space with a point and the point was 0, this is like sort of saying it's 0 outside of a compact region. Okay. So this is I think a fairly reasonable thing to study as a topologist, is compactly supported maps. So this determines a pre-factorization algebra with values in spaces. And note maybe that sort of if U is homeomorphic to Rn, then what it assigns to U is homotopy equivalent to the homotopy equivalent to the n-fold base loops of X, base loop space. So one nice thing about these ideas is that although they're, for me, sort of rooted in trying to understand quantum field theory, they also show up very naturally in other contexts like topology and representation theory. So you can borrow intuition from other subjects. There's sort of this nice transfer of insights. Now, so get back to your main question, for the purposes of QFT, the target category you pick sort of depends on how you're building field theories. So So, if you're doing perturbative QFT, like Feynman diagram stuff, you make some category of sort of topological type vector spaces over power series and H bar or something. I think if you're doing something non-perturbative, then yeah, probably you want some smart choice of topological vector spaces or some cousin thereof as the target. I'm pretty sure Hilbert spaces are a bad choice, but that's like neither here nor there.
It sounds like, yeah, that's why I was asking. Yeah, that sounds good.
I mean, yeah, anyway, to me, as soon as you start trying to really do QFT, you kind of get thrown into some pretty intricate questions of a functional analytic type nature. And it's painful if that's not your favorite thing to do, which it's not mine. But yeah, the target is something you're free to choose. I'm going to just say vector spaces or chain complexes because I don't want to load us up with too much information like that.
Sounds good. Thank you.
Yeah. So
maybe on this point, could we just add something for those listening? Do you hear me?
Yeah, I can hear you worse.
I mean, maybe just since we were talking about Hilbert space, it might be noteworthy that when Haag and Kastler started doing something similar, different but similar in the 60s, they insisted on assigning C-star algebras, right?
Yeah.
Where is the topology of the C-star algebra that really captures the non-perturbative aspect? And then I guess they got actually stuck for decades because they couldn't construct non-trivial examples in higher dimensions. And this idea of dropping this condition kind of led to some progress, but it's perturbative now.
Yeah, so that is a point I was going to bring up in just a few minutes. Sorry, my battery's just getting low. I'm plugging in. I totally agree that I think I agree, Wers. That's a really good point. Maybe we can come back to that in a minute when I've said a little bit more. I'd like to know more before I decide what the target category is optimally. I think this kind of idea, like the Haag-Kastler axioms, is like approximately correct, and maybe they'll end up being even right in the long run. But since we can't turn our favorite examples of QFTs into things that satisfy their axioms, I think we should be open to the possibility that some variation on their ideas is necessary. And I just don't know what the right thing is yet myself.
Oh, absolutely. Yeah, absolutely. I'm just thinking it's just to address Isham's question, I guess that's where the topology came in, but then it was maybe too strict. And now the question is how to relax it again.
Yeah, exactly.
Yeah.
But the sort of reasoning I was doing to sort of motivate the pre-factorization algebra is exactly the same kind of thing Haag and Kastler did to find their axioms up to exactly this target space issue, like you said, target category issue. Okay, so let me mention a good example for sort of developing intuition, and you can do this yourself while you're eating dinner or something in half an hour, is to unpack why, if I have an associative algebra, it determines a pre-factorization algebra on the real line. And let me give you a little hint. Let's call it f sub a. What is f sub a assigned to just an interval? It's going to assign the vector space A. Sort of the only obvious thing to do there is to a single interval assign A. And then the fun part of this example you work out yourself is to see how you can use the way intervals and disjoint set, collections of intervals sit inside of bigger intervals to encode the structure of the associative algebra, like its multiplication map. And so sort of the beginning of a general pattern that sort of allows you to view algebraic structures you already know in this geometric way, thinking about sort of the way shapes, open sets sit inside of a manifold, sort of shapes organize algebra. The 2D picture we drew, you can maybe see a hint of the sort of operator product expansion you might have seen when in CFT or something. Okay, so the upshot is, I hope it's plausible that the observables of a QFT should form a prefactorization algebra. And this is a QFT on a manifold M, which gives you a prefactorization algebra on the manifold M. A question you might ask is, what is a factorization algebra as opposed to a prefactorization algebra? How do I drop the prefix pre? So I'm going to give you a very quick description. It's going to be a little bit highbrow. It's not the focus of the talk, so I don't want to belabor it, but it's not hard to define. So there is a Grothendieck topology on the collection of opens in a manifold M, where the sort of crucial notion is that where the notion of a cover in this setting, we call it a Weiss cover after Michael Weiss, who caught this notion. A Weiss cover U alpha of an open set U is a set of opens such that any finite set of points contained in U is contained in some U alpha. It's my fancy U I used. Okay. So the usual notion of a cover means that if you have one point in U, an element of the cover contains that point, right? That's what it means to be a cover. Every point is contained in some element of the cover. But here we're saying for any finite set of points, there's an element of the cover that contains it. So this is a much stronger condition on a cover. And really the reason you need this is that you want the Weiss cover to sort of contain all the endpoint functions. Sort of the idea is that sort of every set of any tuple finite set of points is contained in some collection of maybe n small disks, one around x1, one around x2, all the way up to xn. And your Weiss cover should sort of know about the structure maps out of such small collections of disks. So this is where we invent this notion of cover, and then definition, a factorization algebra on M is a prefactorization algebra on M. So we have all that data we wrote before. That is a co-sheaf for the Weiss topology. So this means you have all this data we mentioned before, but now it can be reconstructed if you know Weiss covers. So if you know sort of the structure maps on, say, very small disks into bigger disks, you can reconstruct the whole thing. So this is very similar to the way a sheaf is a pre-sheaf satisfying some local to global axiom. So this is just the local to global axiom. Okay. So now I want to revisit that takeaway message and make it a little bit sharper. So so there's sort of two parallel theorems. So let me sort of say, so here's the context, and this is what Urs was bringing up a minute ago. Let me say it sort of amorphously. Perturbative quantum field theory can be made mathematically precise. People have done it in lots of different contexts. And sort of heuristically, what I would like you to have in mind is, that's a really, so here you should imagine you have a manifold M, space-time, the sort of input data, you have maybe V over M, some sort of, say, vector bundle, could be a graded vector bundle. Your fields are smooth sections over M of V, and you have some action functional on fields given in terms of a Lagrangian density. So that's classical field theory. This is sort of the usual Lagrangian field theory. Now fix a solution, phi naught, to the equations of motion for this theory. And you can study what I would call perturbative classical field theory. Equals studying this is the same thing to a mathematician as studying the deformation theory. Of phi naught. So I fixed a solution and I'm studying the ways I can deform that solution to a nearby solution. Sort of perturbation theory in the classical sense of mathematical physics or differential equations. Perturbative quantum theory amounts to some way of integrating in that form around that formal neighborhood. And I just want to say that when I say that it can be made precise, what I mean is that this process, this cookbook that physicists gave using Feynman diagrams, can be turned into a very detailed, careful procedure. You can put renormalization on a solid footing and sort of make this notion like as detailed as you want. So there's two examples that matter to me. Just going crazy with these colors. So in Riemannian signature, Kevin Costello built on work of Axelrod Singer and Kontsevich and others, Catania Felder, K. Costello developed a nice approach applicable to the standard Euclidean field theories. So if you just to be a little bit hand wavy, he really uses some wonderful facts about elliptic complexes, which is a really well developed part of geometric analysis. And he took the sort of process done by physicists, combined it with some nice results from elliptic operators to sort of pin down a nice renormalization process. So if your underlying free theory comes from a de Rham complex, a Dolbeault complex, a Dirac spinner, a Laplace-Beltrami operator, you can apply Kevin's machinery. So this includes Yang-Mills, Chern-Simons, Yang-Mills-Higgs, with a little bit of work, some kinds of sigma models. Pretty great. In Lorentzian signature, there's this lovely renormalization process due to Epstein and Glauser. So it gave us renormalization. They focused on, as far as I understand, kind of the scalar field, but the method generalizes, sort of extended by Friedenhagen and Brunetti. And yeah, maybe crucially for me, as a remark, sorry, this is getting a little bit long-winded. in both cases, there's a version, and this is actually a lot of work, that works compatibly with what's called the Batalin-Vilkovisky formalism, which is a good way to deal with things like gauge theories or supergravity theories. That's what it was originally developed for, as far as I know. And you can do the renormalization in both cases compatibly with the BV formalism. Kevin did this here. In the Lorentzian signature, it was Friedenhagen and Reitzner that did this, as far as I know. Okay, so when I say QFT, I'm going to mean perturbative QFT. I'm going to mean one of these two settings, the theories encompassed by these two formalisms, where perturbative QFT has been set up very carefully. So there's a theorem by Kevin and I, so me with Kevin Costello, and there's a theorem with Kasia Reitzner and I. So this is the, you can imagine what I've just said, this is in the Riemannian signature, this is in Lorentzian signature, but the format of the theorem is similar. So fix classical perturbative theory, I don't know, T classical on M. So we've taken one of these kind of Lagrangian field theories and we fixed a solution to the equations of motion on some manifold M. So if we view a space-time. When you construct these field theories, you actually construct a very precise notion of what you mean by the observables in the theory. So the observables, and I'll write this obs for observables, CL for classical, and sub T form a commutative factorization algebra on M. So not only does it assign a vector space to each open set, it assigns a commutative algebra to each open set. The measurements you can make are just the commutative algebra functions on solutions to the equations of motion in that open set. So it's a commutative algebra. Okay. So classically, of something commutative, if a BV, sort of Batalin-Vilkovisky quantization, oh my God, I really budgeted my time badly. So, okay, is constructed. Okay. Then the observables, let's all write like this, obs Q for quantum for T, form a factorization algebra, not commutative, on M. So I want to make two comments. The first comment is, what this says is that BV quantization produces deformation quantization of factorization algebras. We deform from being a commutative thing to a non-commutative thing in the sense that we stop being commutative on opens. We just are vector spaces. So this is a nice interpretation of Batalin-Vilkovisky quantization, which is some elaborate procedure. From the point of view of the factorization algebras, you start with something commutative and you get something non-commutative. It's some deformation process. The other thing I want to mention is that these quantizations do not always exist. The obstructions are anomalies. So several anomalies that you encounter when you study QFT can be seen quite explicitly as obstructions to producing a BV quantization of a classical theory. Like you just can't quantize it. And the reason why is there's some anomaly. Okay. So, so this is a version of this takeaway message at the very beginning, which is that the factorization algebras capture the observables for perturbative classical theories, and when you can quantize it, captures the observables of the quantum theories as well. They're factorization algebras. Want to remark my notes, it has the following remark. I do not expect that non-perturbative theories give factorization algebras. I think they do give you pre-factorization algebras, but I think this local to global principle breaks down. So I'm happy to talk about that after the talk. But I think this notion of factorization algebra we introduced is really well formed for perturbative stuff, but I don't know what the non-perturbative version is. I guess I should also add a proviso. So Kash and I, when we prove this, we use, we're working within the renormalization procedure that they use for their stuff, and that restricts us to a certain class of Lorentzian theories. There are Lorentzian theories that do not give you factorization algebras, basically because you should not necessarily expect to be able to take a product of observables that are, say, time-like or light-like separated. So Kevin Costello's run into examples of this type of thing. Benini and Schenkel have been studying some examples. So this theorem in the Lorentzian setting is sort of specific to theories where you can do the Epstein-Glaser stuff. Okay, so that was my, that was supposed to be part one. It's really, I guess part maybe 1 and 2. I think I have 15 more minutes. So just because we started a little bit late, but I'm happy to just do 10 if people prefer and stick to the time. What do people think?
No, 15 is fine. We started late, definitely.
Okay, cool. So, so I guess maybe this is supposed to be something like part 3. So yeah, let me remind you over here. Up here, let me just say M is a manifold without boundary. Okay. So a question you should ask, so beyond this setting. So that setting has been very nice. We've spent several communities have spent time studying examples and seeing what parts of physics are captured nicely by this language. But I want to raise another question. There's lots of other features of field theory. Beyond what I've just mentioned. For instance, we could ask about boundary conditions. We could ask about defects. We could ask about dualities. And I guess maybe the first answer is just that we're trying to figure out how to deal with these other things, but we don't have as clean a statement. What I want to do is focus on, I'm going to focus here and mention that then there's an ansatz from physics that lets you construct defects if you know how to make boundary conditions. So I'm going to talk about this. And maybe if people have questions, I can mention at the end a little bit about this. Okay. So trying to figure out how to compress this a little bit. Let me draw a picture first. So let's think about the two-dimensional half space. So I'm picturing here like, so we might just focus our attention for simplicity on open sets that look like disks. So I'm going to erase these lines because they're bothering me. Okay. So this is the half space over here. Okay. There's two special kinds of sort of distinguished opens. There's disks like this that are in the interior. And there's disks that live on the boundary, disk intersecting the boundary. And so you can see that if you take disks in the bulk, so I'm going to call this area out here the bulk, and this is the boundary. Of course, disks in bulk look like, if you want the sort of observables on R2. If you're away from the boundary, you don't really see it. On the other hand, if you pick and open a big disk like this, half disk, let's call it a half disk, that contains the bulk and the boundary, it hits the boundary, then what you see is that the so this that's two, okay, the half disks are sort of modules for the bulk observables. I can multiply things from the bulk with something on the boundary to get another thing on the boundary. So they kind of behave like modules. So this picture where you sort of draw things like this, for TFTs, Kontsevich introduced a language for this, Kontsevich and Voronov, called the Swiss cheese operette. So this is just to orient you. But of course, these pictures make sense in the factorization algebra, the pre-factorization algebra setting. These are just particular open sets, and you have these structure maps. Okay. So what we'd like to do is think about physical situations where maybe you write down a field theory in the bulk using a Lagrangian density. So you have an action functional that sort of gives you equations of motion, but you're also going to need to say what happens along the boundary. So you need to prescribe a boundary condition. So here's the hope. So here's the expectation. So let's let M be a manifold with boundary, and T is a Lagrangian field theory on M. Then we'd expect that, so what is a boundary condition? Well, so here's just, I'm just going to sketch this out very quickly. It's all elaborated in this paper with Eugene and also in his thesis. If you look at solutions to the equations of motion in a small neighborhood of the boundary of M, that's some space. I claim that this is typically a symplectic space. More accurately, it's pre-symplectic, and you can do some kind of reduction. You can also think about solutions to the equations of motion in M. So that's another space. Take solutions on all of M. So let me just draw a picture here. We've got some boundary, and we have some bulk. So here's M, and here's the boundary of M. So if you have a solution to your PDE on this whole space, of course it restricts to a solution since it's a PDE near the boundary. So there's some restriction map here. Let's call this the boundary value. It's just taking the boundary value of the solution. And this was typically symplectic. This is typically a Lagrangian subspace. Okay, so that's the heuristic story. What is a boundary condition? So I should use a different L, straight L. You pick another Lagrangian. I'm going to view this as a boundary condition. So imposing a boundary condition means you pick a Lagrangian in solutions along the boundary, and you ask for solutions in the bulk which have that boundary behavior. So there's a fiber product. These are solutions satisfying the boundary condition. Okay, so this is what I would mean classically by a boundary condition. A good boundary condition is one that's sort of Lagrangian in solutions near the boundary. And you can ask for global solutions with that boundary condition. So an example, let me give you a very, very quick example. Let's do Chern-Simons theory on a 3-manifold M, and I'm going to call the boundary sigma because I equip it with a complex structure. I'm going to use that to make my boundary condition. Well, the Chern-Simons theory, what it really does is I'm going to study, I don't know what's the best way to say this. There's sort of flat G bundles on M is sort of the solutions to equations of motion. You can restrict them near the boundary, and what you get are flat G bundles on sigma. What you could also study are holomorphic, and I guess I pick G as maybe a compact Lie group. I'm going to be a little bit sketchy because I'm sorry, I'm butchering this. Let me just skip this example. I don't think I'm managing it very well. Let me go back to the big picture so that I can at least state Eugene's results. So in the bulk, we know how to construct a factorization algebra by the work we mentioned earlier. So the question is, what should we do on the boundary? It should depend, if we've imposed this boundary condition, it should depend on L somehow. So what we expect is, the expectation is that we get a factorization algebra. I'll call it obs TL on M, where in the bulk, which I'll mean M where you remove the boundary, obs TL, restricted to the bulk, just looks like the observables of T. So there's no boundary condition. But if you take obs TL and you sort of restrict it to the boundary, this does depend on the boundary condition L. So maybe just to mention an example, because I'm running out of time, we do this Chern-Simons example. We can do perturbative Chern-Simons, which only depends on a Lie algebra. I can view it as a complex Lie algebra if I want. G on a 3-manifold, oriented 3-manifold. And I equip this with a complex structure. So here's the picture. Here's M, here's sigma. And the sort of thing that we show is that perturbative Chern-Simons amounts to studying the formal moduli space labeled by the Durand complex on M with coefficients in G. So the more Cartan, the formal space, flat connections are more Cartan elements in this DG Lie algebra. There's a restriction map to Durand forms on sigma, tensor G. That's just restricting to the boundary. But there's an interesting Lagrangian that depends on the complex structure. So these are Dolbeau forms, 1-star forms, and this is a Lagrangian. So this is a Lagrangian, okay? And you can take the fiber product. So this is Chern-Simons with the boundary condition. What this asks for is you're asking for flat connections with the property that along the boundary, they only have a 1-0 part to their connection. Their 0-1 part vanishes. That's what this says. Okay. And you can construct the factorization algebra. And in good cases, you can quantize it. And so obs of Chern-Simons in the bulk, this corresponds to an E3 algebra because it's in the bulk, the factorization algebra of an E3 algebra. And this is sort of equivalent to knowing the quantum group UH bar G. But if you use this boundary condition and you go along sigma, this actually recovers the Katz-Moody, the VOA of an affine Lie algebra, which is some central extension of the loop algebra of G. Both of these things depend on levels, and it's interesting how they match. They cover the sort of level shift people typically talk about here. So this is the kind of thing we're trying to do, capture these ideas, sort of show constructively how these bulk boundary systems are reflected in factorization algebras. And I should say, just heuristically, what Eugene did was he gave for a perturbative classical theory on a manifold M with boundary, there's a technical condition needs to be topological normal to the boundary. So this is a statement about how the equations of motion look. If you pick a collar coordinate, you sort of want the the solutions to sort of propagate topologically in the collar direction. BV quantization and renormalization make sense in the Euclidean case. So he's extending Castella's work, and they give you these sort of stratified factorization algebras in the sense that the observables in the bulk agree with the observables that Kevin and I built. Along the boundary, it depends on the equations of motion. All right, I'm going to stop there. Thank you for listening. And I'm happy to take questions.
Great. Thank you so much, Owen, for the very nice talk. Questions for Owen?
Could you say, Owen, what was the choice of Lagrangian that you made in the previous statement? You said there is a choice to be made for the boundary condition. Which choice was it here?
Like in the Chern-Simons case?
Yes.
So this is an example I was trying to explain.
Oh, there was the choice. I see. Okay, right.
So there's this one here.
So what if you make another choice there?
Yeah, so you can change choices, right? Like you could rotate the complex structures on the Riemann surface, and you could ask how the factorization algebra changes there. Or like if G were, the sort of thing we have in mind typically is something like SL2 or some semi-simple thing, but you could have picked something like a double, like SL2 plus SL2 dual or something. So you could do this for BF theory instead, and then there's other natural boundary conditions that don't depend on a complex structure, that just care about the topological manifold. I can write that out if you want. Yeah, let me just write that out. So I did Chern-Simons. So I did Chern-Simons depending on a complex structure on the boundary. and that complex structure is why we get chiral CFT on the boundary, if you want. We're picking some structure. So changing that complex structure changes the chiral CFT on the boundary a priori, and then you can check how much it depends. But let me do the case of topological BF theory on a manifold with boundary. And this could be sort of any dimension because it's topological BF theory. So if you want to think about it, what is BF theory? The solutions to the equations of motion. BF theory, what they look like is they look like a shifted cotangent bundle. I'm not going to get the shift right, to flat G bundles on M. Okay. Yeah, sorry. So, okay. So if the manifold has boundary, then in fact, I think I can get rid of this. Okay. So to equations of motion on, sorry, no, I did that wrong. There's a shift here. Okay. Then I have solutions to the equations of motion on the boundary of M. And this really does look like the cotangent bundle to flat G on the boundary of M. So this restriction map ends up being a Lagrangian, but this is a symplectic space. It's flat G bundles on the boundary of M, but it's a cotangent bundle. So you could pick, there's lots of choices of Lagrangian. One obvious one is to use flat G bundles on the boundary of M. Another choice of Lagrangian, so that's one Lagrangian, it's called Lagrangian 1. Another Lagrangian is to take a particular flat connection and take its cotangent fiber. This is Lagrangian 2. This is like, in ordinary mechanics, this is like the configuration space is a Lagrangian in the phase space. So that's like the position stuff. This is like the momentum stuff. This is picking a cotangent fiber. And more generally, of course, there's lots of Lagrangians. Like you could take the conormal bundle along some submanifold. Let me give a name, and Y flat G boundary M. Y is something with a map to flat G boundary of M. So if you take the conormal bundle to sort of a submanifold, you get another Lagrangian. So here's 3 different kinds of Lagrangians that show up in BF theory. And each of them leads to different interesting boundary conditions, boundary theories.
Okay, very good. Any other questions? So I have a related question, but maybe simpler. So you get the VOA structure of the affine Lie algebra on the boundary, which is what you expect. But how does the factorization algebra give that? Is it a direct connection?
It's pretty direct. There's some work to do. So let's just, so the case where you get a VOA, really, we should think about the 3-dimensional half space. So we have this boundary wall, and we have this bulk direction, right? So out here, we have these little 3 balls. Along the boundary, we get these little half spheres that you could think about as having to do with disks. Okay.
Okay.
So the boundary here looks like R2, but I've picked a complex structure, so it looks like C. Okay, so let me just flatten that out and look at this copy of C here. I have a factorization algebra, pre-factorization algebra anyway. And so if I pick 2 disks to a bigger disk, I have some map from like sort of the observables. Let's call it D1, D2, and D big. Obs D1, tensor obs D2 to obs of the big disk. And one of the things you can check is, in this case, for this particular boundary condition, the dependence on this product that you're seeing here, if you move these disks around, varies holomorphically. So you could imagine you fix the size of the disks, you have a center point and another point. So that's parameterized by a point Z and a point W. And as you move Z and W around, you could ask how this map changes, and it changes holomorphically. So it really does give you this OPE. And so you can work out these structure maps directly from the construction, and then you just write down the you can extract a VOA from it by looking at the observables in the limit as the disk becomes sort of infinitesimally small. So that's how you get all these Laurent series type things.
This is really, isn't it, Huang's theorem on how vertex operator algebras are algebras for the holomorphic sphere operator, right?
Absolutely. So yeah, Huang encodes it this way. He doesn't write down. Yeah. Basically, this is Huang. We like do Kevin and I in one of our books, we write down a theorem that sort of gives you things you can check about a factorization algebra in R2, like properties or data to check maybe. And if you have a factorization algebra with that data and these properties, there's a functor that extracts a vertex algebra out of it. So like in this case, we just plug in that thing into our theorem and it spits out a vertex algebra, and it is the one for the Kac-Moody Lie algebra. But the principle is, yeah, definitely Huang's theorem.
Okay, very good. Any other questions? Okay, if not, let's thank Owen again for the very nice talk. Thank you very much, Owen.
Okay.